Suppose we have the position time curve being linear in this simple case, and a particle moves from x0 to x from time 0 to time t. Well, the slope of the tangent to this curve in this case is constant, so going this way, we basically took the derivative, and the area under the rate curve, which is the velocity in this case, can be obtained by multiplying this slope by time. The t's cancel and that gives you x minus x0, which is the accumulation of change from time 0 to time t. So the rate of change function can be positive or negative, and in this simple case it's positive, so the accumulated change is positive. And because in this case we have a simple linear function, we're able to evaluate the accumulation of change using simple geometry. The unit for the area under this region is equal to the unit of the rate of change, and that's going to be multiplied by the unit of the independent variable. The seconds cancel, and you get the position in meters. We can approximate the area under a curve in a finite interval using Riemann sums. So with the left Riemann sum, the left of each rectangle touches the curve, and we use the value of the function at these points to obtain the area of each rectangle, and then sum up the areas of each rectangle to obtain the approximation to the area under the curve. Now with the right Riemann sum, the right of each rectangle touches the curve, and similar to the left Riemann sum, we use these values to obtain the area of each rectangle and then sum up those areas. And the midpoint Riemann sum uses the value of the function at the midpoint of each rectangle to obtain the area under the curve. And we can observe that depending on how the function behaves, you may get an underestimate or overestimate to the approximation of the area under the curve. And you may also be given problems in a graphical, numerical, analytical, and verbal form. And we'll develop equations for each of these separate methods and apply them in practice problems. The left Riemann sum can be used to approximate areas under curves, and the left of each rectangle touches the curve. So these values are denoted yi, and in the case where we use rectangles of uniform width, the approximate area is equal to the width of each rectangle, so that would be b minus a on the number of rectangles, and we multiply the width by the height of each rectangle, and sum them together. So that would be the sum from y0 to yn minus 1, because the initial rectangle has a height of y0, and the final rectangle has a height of yn minus 1, as defined by the function of the curve. Now where we choose to approximate the curve using rectangles of non-uniform width, then we basically have a separate width for each y value. So that will be delta xi, which changes for each rectangle. The right Riemann sum approximates the area under a curve over a finite interval using rectangles where the right of each rectangle touches the curve. So if we use rectangles of uniform width, then the width of each rectangle is b minus a on a number of rectangles. And we multiply this by the y values that touch the curve. So effectively we're summing up the area of each rectangle. So here we start with y1, and we end with yn. So as we can see, this here is the initial value, and this here is the final value where the rectangle touches the curve. And similar to the left Riemann sum, we can use non-uniform partitions and multiply each individual y value by a different width. To approximate the area under a curve in a finite interval using the midpoint Riemann sum, we use rectangles where the midpoint of each rectangle touches the curve. So approximating the area using uniform partitions, the width of each rectangle is b minus a on n. Then multiplying this by the y value, at the midpoint of each rectangle, we have y at 1/2, and then plus y at 3/2, and so on, up to y, and the index of this final y value will be y of n minus 1 plus n on 2. So that gives 2n minus 1 on 2. And where we use non-uniform partitions, we can multiply each separate y value by a different width for each rectangle. And we'll see that in example problems. We can also approximate areas under curves over a finite interval using the trapezoidal sum, which can provide a much better approximation. So if we use uniform partitions, we can approximate the area as b minus a on a number of trapezoids. And then if we multiply the width of a trapezium by the average of the heights, so that gives the area of one trapezium, and then we do the same to obtain the remaining areas of the trapezia. So as we can see, only the first and final term are divided by 2, because the middle terms all sum together to cancel out the 2. So we obtain the following approximation to the area. And again, if you had different widths for each trapezia, then you calculate the area of each trapezium using those different widths, and then sum those together to obtain the area under the curve. Let's approximate the area under the curve using the left Riemann sum. So what we have here is 1, 2, 3, 4, and 5. So we're basically dividing this curve into rectangles. And when we take the left Riemann sum, the left of each rectangle touches the curve. So therefore, the area is approximately 5 minus 1 on 4 rectangles. So that's the width of each rectangle. And then we just multiply by the height of the left of each of those rectangles, which is given in a table. So that will be 11 plus 14 plus 19 plus 26. So that gives an area of approximately 70. Let's approximate the area under the curve using the right Riemann sum. So we divide this curve into rectangles, and now because we're using the right Riemann sum, then the right of these rectangles touches the curve. So therefore the area is approximately equal to the width of one rectangle. So that would be 5 minus 1 on a number of rectangles, and that's multiplied by the height of the right of each rectangle that's touching the curve. So that would be 14 plus 19 plus 26 plus 35 as given in a table. So the area is approximately equal to 94. Let's approximate the area under this curve defined by this function over the closed interval from 1 to 5 using the midpoint Riemann sum and 4 uniform rectangles. So basically, when we divide this curve into 4 uniform rectangles, and we're taking the midpoint of each of those rectangles to define the height of each rectangle. So this would look something like this. So therefore the area under the curve is approximately equal to 5 minus 1 on a number of rectangles, which gives you the width of each rectangle. And then we multiply by the sum of the heights of those rectangles, as defined by the midpoint. So over here we have 1.5, so that will be the function f of 3 on 2. Here is 2.5 plus f of 3.5 to get that midpoint, and then plus a function of 4.5 to get that next midpoint. And then evaluate this and post your answer in the comments. Approximate the area under the curve using the trapezoid method. So we have the width of each trapezium as 1, so this is from 1 to 2, then from 2 to 4, and then from 4 to 4.5, and then 4.5 to 5, as given in the table. So these trapezia are going to look something like this, and therefore the approximate area under the curve is the sum of the area of each of those trapezia. So the area of the first trapezium is 11 plus 14 on 2, multiplied by the width of that trapezium, which is 1. And then for the next trapezium, we have 14 plus 26 on 2 by the width of that trapezium, and so on and so forth using the values in that table. So have a go at doing that and post your answer in the comments. Let's approximate the area under the curve given by this function over the closed interval from 2 to 5 using a graphical calculator, and we'll compare the result with that of the midpoint Riemann sum using 3 uniform rectangles. So if we enter the function for our curve and graph it, and then we could do a second function, calculate, and select 7 for the integral, and our lower limit would be 2, and upper limit in the interval would be 5. So that gives us an area under the curve of 69, which is going to be very close to the exact result because the calculator uses a much better approximation. Now if we use the midpoint Riemann sum, then the area is approximately 5 minus 2 on the number of rectangles, which gives the width of each rectangle, and then what you do is multiply this by the function evaluated at the midpoint of each rectangle. And if you plug these values into this equation, and then calculating that out, you get the following result, which is very close to the result we got using the calculator. What we've done so far is partitioned an interval into several rectangles, whether they be non-uniform or uniform, and each rectangle has a width delta xi, and we multiply this by the value of the function at xi, which depends on which method we used, such as the left, right, and midpoint Riemann sum. Now if we take the limit, as the width of the largest partition tends to 0, or where the number of rectangles we use tends to infinity, So in the limit, the width of each rectangle becomes infinitely small. So that becomes dx, and then we multiply this by the value of the function f of x, which gives the area of the infinitely thin rectangle, and then we integrate from a to b. And that is basically summing up the areas of all these rectangles from a to b. And this here is what we call the definite integral, which gives us the exact value of the area under a curve in the closed interval from a to b. Now you may be given a definite integral and then be asked to translate it into a Riemann sum. And here we'll illustrate the process using a left Riemann sum. So what we do first is partition a domain over some number of rectangles. And then we sum the areas of each rectangle from some I value to n or n minus 1, depending on which method we use. Now using the left Riemann sum, we want to multiply the width of each rectangle by the value of the function on the left of each rectangle. So we have f of a plus the width of each rectangle, and multiply that by the index I. So for the left Riemann sum, we initially want I equals 0, and then sum to I equals n minus 1. And you can see that when I equals 0, we get f of a, and then when I equals 1, we basically evaluate the function at a plus the width of each rectangle. So this basically gives us the approximation to the area under the curve using the left Riemann sum. Demonstrate your understanding of the definite integral using the diagrams below and the left Riemann sum. So for the left Riemann sum, we have the height of the left of each rectangle being f of xi, and the width of each rectangle being delta xi. And then multiplying them together gives the area of one rectangle, and then summing through over all the rectangles gives the approximation for the area. Now if we keep decreasing the width of each rectangle, so in other words in the limit, as the number of rectangles become infinity, and we're taking the limit of the left Riemann sum, so this is the same thing as taking the limit as delta xi approaches 0. So we end up with rectangles of infinitesimal width dx, and the height's simply going to be f of x. And therefore we can write this sum as the integral of f of x with respect to x, which gives the area of that infinitesimal rectangle, and we're integrating from a to b. Let's translate this definite integral to a right Riemann sum. So recall with a right Riemann sum, the right of each rectangle touches the curve. And we'll assume rectangular partitions with a uniform width. So given the interval we're looking at from 4 to 7, the width of each rectangle is 7 minus 4 on the number of rectangles. And now we can sum the area of each rectangle, which is the width of each rectangle, which we can take out of the sum because it's constant, and then we'll multiply that by the height of each rectangle. So that will be x squared plus 10, or 4 plus the width of each rectangle multiplied by the index I, squared plus 10. And for the right Riemann sum, we sum from I equals 1 to n. And you can convince yourself that this makes sense by selecting some specific number of rectangles and then calculating the value in the brackets and making sure you get the correct values between 4 and 7 for each value of I. If we have a continuous function that's differentiable, then the area under the rate function gives us the accumulation of change over the interval from a to x. And this is represented by a definite integral. So in other words, f is the antiderivative of its derivative. So now if we replace the derivative with the function, then this here is the antiderivative of the function, and therefore this expression can be written as follows. And if we replace x in the integral with a dummy variable, we won't alter the result, because after you evaluate the integral, you'd substitute x for t. And now if we differentiate both sides, well, on the left hand side, the derivative of the antiderivative is the original function, and that's equal to the expression on the right hand side. So this tells us that the derivative of the integral, or antiderivative of the function, is equal to the original function. And that's the fundamental theorem of calculus applied to accumulation functions. There are multiple ways accumulation functions can be represented, and this here is the analytical representation, which tells us that the area under the curve of the function f from a to x, so for example if a equals 2 and x is anywhere, then this is the area that keeps accumulating as we move x to the right. So effectively what we'd get is g of x minus g of 2. And for the special case where the function evaluates to 0 at a, then we can get rid of this term. So this is the graphical representation, and we can also have numerical representations. So in this case, we can actually calculate the area under the curve from 2 to x using the area of a trapezium. So taking the average heights of the trapezium, and then we multiply by the width of the trapezium. And that'll give you a general expression for g of x. And this is the same as the area that'll be given by the definite integral, and we'll show that when we learn how to evaluate definite integrals. We've seen that definite integrals are used to obtain areas under curves, and before we go through methods to evaluate them, we'll look at some basic properties of definite integrals. So if we integrate a constant multiplied by a function, then we can take the constant outside the integral. And the integral of the sum of two functions, or the difference between two functions, can be broken up into two integrals. So we integrate the first function, and then we add or subtract the integral of the second function. And we can also reverse the limits of integration. So if we integrate from a to b, we can negate the integral and reverse the limits. So in other words, we can integrate from b to a. And we can also break up an integral into several integrals. So suppose I want to integrate from 3 to 5. I can first integrate from 3 to 4, and I can continue the integral from 3 to 5. And that's going to give me this area under the curve. So in other words, we integrate from a to c, and then from c to b. We can also use definite integrals to find areas under curves where there's removable and jump discontinuities. So where there's a removable discontinuity, we can still apply the definite integral in the same way, because as you can imagine, even though the function does not exist at c, the area at a point is infinitely thin, so it's not going to affect the result. Now with a jump discontinuity, we can evaluate the integral piecewise to find the area under each curve to both sides of the discontinuity. So we can integrate from a to c first, then we can add the area from c to b, so to obtain that, we'll integrate from c to b. We previously wrote the definite integral in the form of an accumulation function. So for a continuous function on an interval that contains a, then the area under the curve of that function is equal to the accumulation of change. So effectively, capital F is an antiderivative of the function f. So in a similar way, for a continuous function on the interval from a to b, the area under the curve of the function in that interval can be written using a definite integral. So effectively, evaluating this integral is the same as taking the difference in the antiderivative evaluated at a and b. And that's a fundamental theorem of calculus applied to definite integrals. The rules of differentiation are really the foundation for finding antiderivatives. So here we differentiate x to the power of n with respect to x, and by the power rule, we put down the exponent and then subtract 1 from the exponent. And here we've also included a constant, which disappears when you differentiate. Now to go in the opposite direction, what we do is separate dx and then integrate both sides. So effectively, the integral of the differential gives us back x to the n plus c, and we call this an indefinite integral because it doesn't have limits of integration, but finding the antiderivative is similar for definite and indefinite integrals. So in general, if we have an integral of x to the power of n with respect to x, we add 1 to the exponent and divide by the resulting exponent, and add a constant of integration. Where n is not equal to -1, well, we got to divide by 0. And this here is the power rule for integration. We can also apply the rules for differentiating elementary functions to give us a clue on how to integrate them. So using this one as a guide, we can obtain the integral of sine of a constant by x. So when we differentiated, we multiplied by k and negated the result. So when we integrate, we divide by k and negate the result. And where we have an indefinite integral, we add a constant of integration. Now we can evaluate the integral of cosine a constant by x in a similar way. So here when we differentiate, we don't have a negative sign. So we simply divide by k and multiply by sine kx. And the other integrals are obtained in much the same way. We can also use the derivatives of the other trig functions as a guide to obtain their antiderivatives. So differentiating tan of a constant multiplied by x, we multiply a constant by sec squared kx. So that tells us how to integrate sec squared kx. So we effectively divide by k and multiply by tan kx. And where we have an indefinite integral, we add a constant of integration. And a similar result can be obtained by integrating cosec squared kx. So when we differentiated the cotangent, we multiplied cosec squared kx by a negative constant. So to obtain an antiderivative, we have minus 1 on k by the cotangent of kx plus a constant of integration. And similarly, if we want to integrate this result on the right, and in a similar way, we can integrate cosec kx by the cotangent of kx. We can also use the derivatives of inverse trig functions, which were derived earlier, to obtain the antiderivatives of reciprocals of radicals and reciprocals of polynomials. So integrating 1 over the square root of 1 minus x squared with respect to x is basically just going backwards to arcsine. And where we have an indefinite integral, we add a constant of integration. And in a similar way, you can integrate these expressions on the right to give you the results on the left. And sometimes this integral may not be perfectly aligned with 1 over the square root of 1 minus x squared, so we'll introduce other integration techniques later on, such as completing the square, to generally get the integral in this form. And the same thing applies to this integral, for example. So this will directly give you the arctan of x plus a constant of integration, but you may get 2 on 2 plus x squared, and so on, and you might need to do a bit of algebra to get the integral in this form. We can also use the derivatives of logarithms and exponential functions to obtain the antiderivatives. So remember when y equals log base a of x, we took a to the power of both sides, and then we took the natural log of both sides and divided by the natural log of a. So if we wanted to integrate 1 over x by the natural log of a, then you can take the constant outside the integral. So this will give you the natural log of x on the natural log of a plus a constant of integration. And as we can see, that's equal to y, which is log base a of x. So effectively this expression is the same as this one over here. And we can also use this derivative to integrate exponential functions with a base a. What we do is divide by the natural log of a and multiply by a to the x and add a constant of integration. And we'll get some practice using all these rules for finding antiderivatives. Let's evaluate the following accumulation function. So if we evaluate this integral using the first fundamental theorem of calculus, we get t cubed evaluated from 1 to x, and therefore g of x is equal to x cubed minus 1. So if we plot this function here, it looks something like this. So we're integrating from 1 to x, and the function just accumulates as x moves to the right. So at x equals 4, what we get is 64 minus 1, which is 63. Let's evaluate the accumulation function at x equals pi and 2 pi. So if we integrate this, what we get is minus cosine t, evaluated from 0 to x. And that's thereby equal to minus cosine x minus cosine 0, which is plus 1. So note that the sine function can be plotted like this. So it's equal to 1 at pi on 2 and minus 1 at 3 pi on 2. And the function is accumulating the area from x equals 0 to some x over here. So at x equals pi, we have f of pi is equal to minus 1 plus 1, which is 2. And then to 2 pi, we get an accumulation of 0, because we have a positive area and an equal negative area here which cancel out. Let's evaluate the accumulation function at x equals 3 pi on 2. So we get sine t evaluated from pi to x. So that gives g of x is equal to sine x minus sine pi, which is 0. So if we plot cosine x, it looks something like this. So at x equals pi on 2, cosine is 0, and at 3 pi on 2, cosine is 0. And it's equal to minus 1 at pi. So since the function is accumulating from x equals pi to some x over here, well, what we get is g of 3 pi on 2 is equal to minus 1. Okay, because the function is evaluated using this area over here, from pi to 3 pi on 2. Let's evaluate this integral. So it looks like a simple application of the power rule, because this term here is x to the minus a half. So therefore, we get 3 by x to the 4 on 4, plus x to the 1 half on 1 half, which is 2x to the half, and then plus 5x, and plus the constant of integration. Let's evaluate this integral. So one thing you may recognize is the derivative of cosec a constant by x is equal to minus k cosec kx by the cotangent of kx. So if we divide through by minus k and then integrate both sides, where this here is the integrand, well, what we get is minus 1 on k. So this time we have minus 1 on pi on 4, which is 4 on pi, and cosec pi on 4x, plus the constant of integration. A common technique to evaluate antiderivatives is use substitution. So suppose we have an antiderivative of some function f, which is a composite function of u of x. Well, using the chain rule, we can differentiate the antiderivative with respect to x. So what we get is the derivative of the antiderivative with respect to u, which is f of u, and du dx is u dash of x. And now if we separate dx and then integrate both sides of the equation, then what we get is the antiderivative as a function of x. And we can write this in another form. So du dx is du. And this is the form when use substitution is applied. So from this expression, use substitution works where we have the function of u multiplied by the derivative of u. And we'll see that in several examples. We've seen that use substitution can be applied to indefinite integrals, where we're integrating a composite function of u multiplied by the derivative of u. And this basically gives us the antiderivative by reversing the application of the chain rule. Now where we have a definite integral, and we're integrating with respect to x, we're going to integrate from some x equals a to another x equals b. So when we apply use substitution to a definite integral, we need to change the limits of integration. And remember that u is a function of x, so we instead integrate from u of a to u of b. And this will become more clear when we look at example problems. Let's evaluate this integral. So we can see that we cannot apply use substitution, so we'll simplify the integral algebraically by multiplying by e to the minus x on e to the minus x. So if we take 5 outside the integral because it's a constant, we have e to the minus x over e to the 0, which is 1, plus 8e to the negative x. And this is evaluated with respect to x. And now we can use use substitution. So if we let u equal 1 plus 8e to the negative x, then du is equal to minus 8e to the minus x dx. And therefore we can rewrite this integral as 5 by the integral of e to the minus x dx, which is minus du on 8, and that's divided by u. So evaluating this integral, we get minus 5/8 by the natural log of u, which is 1 plus 8e to the negative x plus the constant of integration. Let's evaluate this integral. So you may recognize that the derivative of tan x is sec squared x. So if we let u equal tan x, then du is sec squared x dx. And therefore this integral becomes the integral of tan x, which is u, by sec squared x dx, which is du. And therefore this evaluates the u squared on 2, so it'll be 1/2 u squared, where u is tan x, so we get tan squared x, plus the constant of integration. Let's evaluate this integral. So this time these terms are not derivatives of each other, so we can write this as the integral of 1 over cosine pi x, and tan x is sine pi x on cosine pi x. So now we can set u equal cosine pi x, then du is equal to minus pi sine pi x dx. And therefore we can rewrite this integral as sine pi x dx, which is minus 1 on pi du, and u equals cosine x, so therefore we can write u squared. And evaluating this integral, we have u to the minus 2, so we have minus 1 on pi by u to the minus 1, on minus 1 plus the constant of integration, and therefore we end up with 1 over pi by 1 on u, which is the same thing as sec pi x plus the constant of integration. Let's evaluate this integral so we can try to manipulate it to apply u substitution. So cosec squared 2x is 1 over sine squared 2x, and we can multiply this by 1 over cosine squared 2x on 1 over cosine squared 2x. So we can rewrite this as sec squared 2x in a numerator, and in a denominator we have tan squared 2x integrated over x, and now we can use u substitution. So u is equal to tan 2x, and therefore du is 2 sec squared 2x dx. And we can substitute for this term in a numerator, so that gives the integral of du on 2, and in the denominator we have u squared. So integrating u to the minus 2 gives you u to the minus 1 on minus 1. So what we get is minus 1 half by 1 on u, which is 1 on tan 2x, or the cotangent of 2x plus c. Let's evaluate the derivative of the cotangent of x. So using trig identities, we can write this as a cosine on the sine of x, integrated with respect to x, and then using u substitution, we can let u equal sine x, and then du is cosine x dx. And therefore we can write this as the integral of du on u, which is a natural log of u, where u is sine x, plus the constant of integration. Let's evaluate the integral of 1 over x by the natural log of x. Well, we can let u equal the natural log of x, then du is equal to 1 on x dx. And therefore we can write this as the integral of du on u, which is equal to the natural log of u plus the constant of integration, where u is the natural log of x. Let's evaluate this integral. So we can let u equal cosine x, then du is minus sine x dx. And therefore we can write the integral as the integral of 5 to the u with respect to u, but we have a minus there. And therefore this evaluates to minus 1 over the natural log of 5 by 5 to the u, which is 5 to the cosine x plus the constant of integration. Let's evaluate this integral. So we can write this as the integral of x squared over 1 plus x cubed all squared. And now we can set u equal to x cubed, then du is 3x squared dx. And now we can write this integral as 1/3 du over 1 plus u squared. And that's equal to 1/3, and you may recognize this as arctan u. And u is equal to x cubed plus the constant of integration. Let's evaluate this integral. So we can write this as the integral with respect to x, and in the denominator we can factor out 16, so we have 1 minus x on 4 squared. And therefore we have 1/4 by the integral with respect to x on the square root of 1 minus x on 4 squared. And if we let u equal x on 4, then du is 1 on 4 dx. And therefore what we end up with is 1/4 by 4, which is the integral of du over the square root of 1 minus u squared. And you may recognize this as the arc sine of u, so we get the arc sine of x on 4 plus the constant of integration. Suppose we have the integral of a rational polynomial function, so the polynomial in the numerator can be written as follows, and similarly we can write the polynomial in the denominator as follows. Now for the case where the order of the polynomial in the numerator, or the degree of the largest term, is greater than or equal to the order of the polynomial in the denominator, well, we can apply polynomial long division to simplify the integral by rearranging it into an equivalent form. And this will be clear when we cover some examples. We can also complete the square to simplify integrals by rearranging them in their equivalent forms. And the main two types of integrals we'll look at are reciprocals of radicals of quadratic polynomials, or the reciprocals of quadratic polynomials. So P2 can be written as follows. And when we complete the square, to put these integrals into their equivalent forms, they typically evaluate to known inverse trig functions. And we'll see that in several examples. Let's evaluate this integral. So we have the polynomial in the numerator having a higher degree than the polynomial in the denominator. So what we can do is use polynomial long division to simplify this integrand. So x into x squared goes x times by x is x squared, and 1 by x is x. And we subtract those, and what we end up with is minus 6x plus 5, and then x into minus 6x goes minus 6 times, by x is minus 6x, and then minus 6 by 1 is minus 6. And then we subtract those from each other, and we end up with 11 for our remainder. So therefore this integral can be written as x minus 6 plus 11 on x plus 1. And now you should find this easy to integrate, and post your answer in the comments. Let's evaluate this integral. So in this case, the degree of the polynomial in the numerator and the denominator are equal. So therefore we can use polynomial long division, or alternatively we can simplify this integral as follows. So I have x squared plus 5, and then minus 6 in the numerator gives us minus 1. And that's divided by x squared plus 5, and we integrate with respect to x. And therefore we can write this integral as the integral of 1, because x squared plus 5 on x squared plus 5 is 1, and then minus 6 on x squared plus 5. And this is integrated with respect to x. And as a hint, this second part of the integral is going to be an arctan. So evaluate the integral and post your answer in the comments. Let's evaluate this integral. So the degree of the polynomial in the numerator has a higher degree than the polynomial in the denominator. So what we can do is use polynomial long division. And because we don't have an x squared term, we can just put 0x squared. Now x into x cubed goes x squared times, by x is x cubed, then x squared by 1 is x squared, and we subtract the result, and that gives us minus x squared. And now we bring down the 3x term, and x into minus x squared goes minus x times, multiplied by x is minus x squared, and minus x by 1 is minus x. And then subtracting the result, which is minus 2x. Then bring down a 6, and then x into minus 2x goes minus 2 times, by x is minus 2x, and then minus 2 by 1 is minus 2. And then subtracting the result, we obtain 8. And therefore we can write the integral as follows. So x squared minus x minus 2 plus 8 on x plus 1. And now you can integrate this quite easily and post your answer in the comments. Let's evaluate this integral. So because we have a radical, we can try to complete the square. So we have minus x squared plus 2x minus 6. And we complete the square by writing x squared plus 2x, and then divide this by 2 and square it. So we get 2 on 2 squared, and then to get minus 6, we subtract 7. So therefore we can write this as 7 minus x plus 1 all squared. And therefore if you replace this polynomial with this term over here, and then you can use U substitution to evaluate an arcsign for a solution. And I'll leave it for you to post your answer in the comments. Integration by parts can be applied to find the antiderivative of a function that's a product of two functions. And this is done by reversing the product rule of differentiation. So if we separate delta x and integrate both sides, well, on the left hand side, the integral of the differential of a function gives us back that function, and on the right hand side we end up with the following integrals. And rearranging the terms, and we'll apply this method using several examples where we have the integral of a function which is generally a product of two different functions. Let's evaluate this integral. So we can't really simplify this algebraically or use U substitution, so we'll do integration by parts. So if we set u equals the natural log of x, because we don't want to integrate this, then du is equal to 1 on x dx. And we can set dv is equal to dx, or 1 by dx. And therefore v is equal to x. And now we multiply u by v, and minus the integral of v by du. So x by 1 on x is 1, and we integrate over x. So therefore we obtain x by the natural log of x minus x plus the constant of integration. Let's evaluate this integral of two functions that are not the derivatives of each other. So we can't use u substitution, and we'll therefore try integration by parts. So we're going to set u is equal to x squared, and du is therefore 2x dx, and dv is cosine x dx, and therefore v is equal to sine x. So u multiplied by v gives x squared sine x minus the integral of v by du. So that will be 2x sine x dx. And now you can apply integration by parts again to evaluate this integral, and add the constant of integration and post your answer in the comments. Let's evaluate this integral, which is a product of two functions that are not the derivatives of each other. So we can't apply u substitution, and will thereby apply integration by parts. And because the integral of e to the x does not change, we're just going to set u is equal to x and eliminate the x. So what we get is du is equal to dx, and setting dv equal to e to the x dx, we obtain v is equal to e to the x. And therefore the integral becomes u multiplied by v minus the integral of v by du. So what we obtain is x e to the x minus e to the x plus the constant of integration. Let's evaluate this integral. So again, we're going to use integration by parts because we can't apply integration by substitution or simplify this algebraically. So we can set u equal to either of these functions because they're going to keep oscillating back and forth when we differentiate or integrate them. So what we get is du is cosine x dx, and setting dv equal to e to the x dx, we get v is equal to e to the x. So therefore u by v is e to the x sine x minus the integral of v du. And therefore what you do is perform integration by parts on this integral again, and you'll get this in the form of e to the x sine x, and then you can set the result equal to this result and solve for the integral. So I'll let you try that yourself and post your answer in the comments. Let's evaluate this integral, which is a product of two functions that are not derivatives of each other. So what we'll do is use integration by parts and set u equal to the natural log of x to avoid integrating it. So we get du is equal to 1 on x dx, and therefore dv is x dx, and v is therefore x squared on 2. So u multiplied by v gives x squared on 2 by the natural log of x minus the integral of v du. And therefore one of the x's cancel, so what we get is x squared on 2 by the natural log of x minus this integral, which gives x squared on 4 plus the constant of integration. Let's evaluate this integral. So again, we're going to use integration by parts because we can't employ u substitution. But in this case, I'm going to set u equal to x because we want to reduce the power of x. So we get du is dx, and dv is sec squared x dx, and integrating this is going to give tan x. So therefore u multiplied by v minus the integral of v du, which is the integral of tan x with respect to x. And you can evaluate this integral using u substitution, and you'll obtain the following result. So we get x by tan x minus minus, which is a plus, the natural log of cosine x plus the constant of integration. We can use partial fractions to decompose an integral into a simpler form with the degree of the polynomial in the numerator is smaller than that in the denominator. Here we have distinct linear factors in the denominator, so we can rewrite the integrand as follows. Effectively decomposing it into the sum of two constants divided by each separate factor. And now if we multiply through by x minus a by x plus b, we obtain the following expression. And now you can set x equals a to get rid of this term, and that'll give you the following equation. And then you can solve for a, and similarly if you set x is equal to minus b, we get rid of the left term, and we obtain the following equation, which you can solve for the constant b. And now integrating this sum is much easier than integrating this term. In this case, we have a rational polynomial function where the degree of the polynomial in the numerator is smaller than that in the denominator, but we have a repeated linear factor in the denominator. So we can rewrite this integrand as follows. So effectively we decompose the integrand into the sum of a constant on a distinct linear factor, and for the repeated linear factor, we have a constant on the power of each factor. So b on x plus b and c on x plus b squared. And now we can follow the same procedure by multiplying through by the factors in the denominator. So we obtain the following expression. Now if we set x is equal to a, well this term disappears and so does this term. And then we can solve for the constant a, and in a similar way we can set x is equal to minus b, and then we can solve for c, and then you can equate the coefficients of x and obtain b. And once we find those constants a, b and c, this sum is much easier to integrate than this rational polynomial function over here. We have a rational polynomial function where the degree of the polynomial in the numerator is smaller than that in the denominator, but we have an irreducible quadratic factor in the denominator. So we can use partial fractions to simplify the integrand as follows. And for the irreducible quadratic, we write ax plus b on the irreducible quadratic factor. So as you can see, the degree of the polynomial in the numerator is still smaller than that in the denominator. And then for the distinct linear factor, we add another constant on x plus b. And now if you multiply through by the factors in the denominator, we obtain the following expression. And now if you set x equal to minus b, this term disappears, and we end up with the following expression. And you can solve this for c, and you can equate coefficients to obtain the remaining constants. So I'll leave that for you as an exercise. And then integrating this sum is much easier than integrating this rational polynomial function. In this integral, the degree of the polynomial in the numerator is lower than that in the denominator. So we can use partial fractions, and we can try to factorize the polynomial in the denominator. So what we get is x minus 2 and x plus 3. And because we have distinct real factors, we can write the partial fraction as some constant on x minus 2 plus another constant on x plus 3. And if we multiply through by the denominator, well, what we get is 3x plus 2 is equal to a by x plus 3 plus b by x minus 2. And if we set x is equal to 2, then what we get is 5a is equal to 6 plus 2 is 8, so a is equal to 8/5. And similarly, you can also equate coefficients. So the coefficients of x are a plus b is equal to 3, and if you sub for a, you'll get b. And therefore you can write the integral in this form and easily evaluate it. Let's evaluate this integral. So we have the degree of the polynomial in the numerator is lower than the degree of the polynomial in the denominator, and we have a repeated linear factor in the denominator, so we can write the following partial fraction. So a on x plus 1 plus b on the second power of x plus 1. And now we can multiply through by x plus 1 squared. So we get 3x plus 2 is equal to a by x plus 1 plus b. And now we can set x equal to minus 1. So what we get is b is equal to minus 3 plus 2 or minus 1. And if we equate coefficients of x, we get a is equal to 3. And as we can see, the integral becomes much easier to evaluate when it's in this form. Let's evaluate this integral. So the degree of the polynomial in the numerator is smaller than that of the polynomial in the denominator, so we can use partial fractions. And what we have is a repeated linear factor, so we write a on x plus b on x squared, and then plus a distinct linear factor, so we have c on x plus 1. And now if we multiply through by the denominator, we get 3x plus 2 is equal to a by x by x plus 1 plus b by x plus 1 plus cx squared. And now we can set x equal to minus 1, so that eliminates a and b. So what we get is c is equal to minus 1. And if we set x equal to 0, we eliminate a and c, so what we get is b is equal to 2. And you can obtain c by equating coefficients of x squared. So we have ax squared plus cx squared is equal to 0. So therefore a is equal to minus c, or 1. And now the integral becomes much easier to evaluate in this form. Let's evaluate this integral. So we have the degree of the polynomial in the numerator is smaller than the degree of the polynomial in the denominator. And what we have first is an irreducible quadratic. So we write ax plus b over x squared plus 1. And we have a distinct linear factor, so we can write c on x minus 3 as our partial fraction. And then multiplying through by the denominator, we get 3x plus 2 is equal to ax plus b. That's multiplied by x minus 3 plus c on x squared plus 1. And now if we set x equal to 3, we eliminate the first term, so what we get is c multiplied by 10 is equal to 11, so c is equal to 11 on 10. And I'll leave it for you to equate coefficients, and then you'll be able to get a and b, and therefore the integral in this form becomes a lot easier to evaluate. And post your answer in the comments. Let's evaluate this integral. So the degree of the polynomial in the numerator is smaller than that in the denominator, so we can use partial fractions. And we can further factorize the denominator, so we have 3x on x squared by x minus 1 on x plus 1. So what we have is a repeated linear factor, so we write a on x plus b on x squared, and two distinct linear factors, so we have c on x minus 1 plus d on x plus 1. And now we can multiply through by the denominator, so we get 3x is equal to ax by x minus 1 by x plus 1, and then plus b by x minus 1 by x plus 1, and then plus c by x squared by x plus 1, and then plus d by x squared by x minus 1. And now you can set x is equal to 1, x is equal to minus 1, and equate coefficients, and you'll be able to get these constants, and the integral becomes a lot easier to evaluate. And post your answer in the comments. An integral is improper if one or both limits of integration are infinite, or the integrand is unbounded in the interval of integration. So in this case, the natural log of 0 is undefined. So we can use limits of definite integrals to evaluate these improper integrals. So for the first example, we replace infinity with a dummy variable that approaches infinity, and then the integral is written as follows. And then you evaluate this definite integral and then take the limit to obtain the result. Now when we have both limits of the integral being infinite, we can evaluate this integral piecewise. And you can use the same method to introduce a dummy variable, evaluate the integral and then take the limit. And similar with this third integral, we can introduce a dummy variable. So this approaches 0 from the right hand side, where the natural log of x is defined. And then you can evaluate the definite integral and take the limit to get the result. And we'll cover several examples. Let's determine if this integral converges. So we know there's a discontinuity at x equals 0, so we need to evaluate this integral piecewise. So we evaluate from minus 1 to 0 from the left hand side, and then plus the integral from 0 from the right hand side to 1. And because these are improper integrals, because the integrand goes to infinity when we sub 0, so we use dummy variables. So in other words, we take the limit as a dummy variable goes to 0, and replace this limit of integration with the dummy variable. And we do the same for this integral. And now what you do is evaluate the integral, take the limit to determine if the integral converges, and post your answer in the comments. Let's determine if this integral converges. So what we have is an improper integral because we have a limit of integration that's infinity. So we replace that with a dummy variable and take the limit as a dummy variable goes to infinity. So effectively we're integrating from 2 to b, and our integrand is 1 on x squared. And now we can basically evaluate this integral, so we get minus 1 on x, evaluated from 2 to b, and we take the limit as b goes to infinity. So what we obtain is the limit as b goes to infinity, of minus 1 on b minus minus a half. So when b goes to infinity, this term disappears, and therefore we obtain 1 half, and therefore the integral converges, because we obtained a finite value. Let's determine if this integral converges. So we have an improper integral because we have a limit of integration that's infinity, so we replace this with a dummy variable and take the limit as a dummy variable goes to infinity. And because we have a constant, we can take the constant outside. So what we have is 1 over 1 plus x squared evaluated over x. So this integral evaluates to an arctan, so we have 3 by the limit as b goes to infinity. And we have arctan of x evaluated from 0 to b. And therefore we have 3 by the limit as b goes to infinity of arctan b minus arctan 0. And arctan 0 is 0. And as b goes to infinity, arctan b approaches pi on 2. So what we get effectively is 3 pi on 2, and therefore the integral converges. Let's determine if this integral converges. So we have an improper integral because we have a limit of integration. So we take the limit as a dummy variable goes to infinity and replace the limit of integration with that dummy variable. And we evaluate that integral and then take the limit. So using u substitution, you'd obtain the following result when you evaluate that integral. So we have the natural log of x minus 1 evaluated from 2 to b. And therefore we have the limit as b goes to infinity of the natural log of b minus 1 minus the natural log of 2 minus 1, which is 1. And the natural log of 1 is 0. And as b goes to infinity, this is going to go to infinity, and therefore the integral diverges. Let's determine if this integral converges. So if we plug in x equals minus 3, the integrand goes to infinity. So therefore this is an improper integral, and we thereby replace the limit of integration with a dummy variable. And we approach 3 from the right hand side. And think about why that is. So we evaluate the integral from b to 2, and we have 1 over root x plus 3. So you can use u substitution to evaluate this integral. So what we get is the limit as b approaches minus 3 from the right, and this evaluates to 2 root x plus 3 evaluated from b to 2. And what we get is the limit as b goes to minus 3 from the right hand side of 2 root 5 minus 2 square root b plus 3. And as b goes to minus 3, this term disappears, and what we obtain is 2 root 5. So therefore the integral converges. Let's determine if this integral converges. So if we substitute 0 into the natural log, you're going to get an infinite value. So therefore we can use a dummy variable and take the limit as b goes to 0 from the right hand side where the natural log is defined, and we integrate from b to 3. And now if you evaluate this integral by parts, you're going to get the following result evaluated from b to 3. And therefore we get the limit as b goes to 0, and 3 squared on 2 is 9 on 2 by the natural log of 3, and then minus 3 squared on 4, and minus b squared on 2 by the natural log of b, and then plus b squared on 4. Now as b goes to 0, this term disappears, and if you use L'Hopital's rule, this limit here is going to evaluate to 0. So verify this, and therefore the integral converges to 9 on 2 by the natural log of 3 minus 9 on 4. Let's summarize a general procedure for selecting integration methods on the level of AP calculus. So first we try the power rule, and then we can try u substitution, which applies if a function is a derivative of another. And if we have a more complicated integral, we can try to apply some algebra to simplify it. And if we have a rational polynomial function, then we can apply partial fractions. And if we have some polynomial with a constant in a numerator, then we can complete the square to evaluate the integral using inverse trig functions. And polynomial long division applies to a rational polynomial function, and we can apply trig substitution where we want to simplify the integral that has a radical in it, or a polynomial with x squared plus 1 and so on. And trig identities can be applied to simplify trig functions, And where we run out of options, we really apply dummy variables to simplify the integral. And where we have the product of two functions that are different, then we can apply integration by parts. So post your thoughts in the comments of how you would actually apply these procedures. Let's evaluate this integral. So on first glance, you may want to use partial fractions because the degree of the polynomial in the numerator is lower than that in the denominator. But we can't really factorize the polynomial in the denominator, so we need to do a bit of algebra. So if we recognize that if we differentiate the polynomial in the denominator, we're going to get 2x plus 1, so we can somewhat apply u substitution. So we have 2x plus 1 plus 4, and that's divided by the polynomial in the denominator. Okay, so we can evaluate these integrals, and that's the same thing as evaluating this one. So the first one, we can use u substitution, and in the second one, we'd complete the square and get an arctan. So what we can do is write x squared plus x plus 1 on 2 squared, and then 1/4 plus 3/4 is 1. So this can be written as x plus 1/2 all squared plus 3/4. And now you can evaluate this to an arctan using u substitution and a bit of algebraic manipulation. And post your answer in the comments. Let's evaluate this integral. So what we'll do first is take the constant outside the integral, and we can apply trig identities to simplify this, but it's not quite there yet. So what we do is multiply by the conjugate in the numerator and the denominator. And therefore what we get is 1/2 by the integral of 1 minus sine x over 1 minus sine squared x, which using the trig identity gives cosine squared x. And now we can separate this integral into two, so we have 1/2 over 1 on cosine squared x, or sec squared x, minus 1/2 by the integral of sine x on cosine squared x. So to evaluate the second integral, we can apply u substitution, and for the first integral, we can multiply it by 1 on sine squared x over 1 on sine squared x. So you'd get a cosec squared in the numerator and a cotangent squared in the denominator, and from that you can apply u substitution and evaluate this integral. So post your answer in the comments. Let's evaluate this integral. So using a bit of algebra, we can write it as the integral of sine squared x by sine x integrated with respect to x. And we can further do a bit of manipulation. So using the trig identity, we have 1 minus cosine squared x by sine x dx. And let's further split this into two integrals. So we have the integral of sine x with respect to x minus the integral of cosine squared x by sine x dx. So this integral you can evaluate quite easily, so it's minus cosine x, and this one you can quickly evaluate using u substitution. So post your answer in the comments. Let's evaluate this integral. So the functions here are derivatives of each other, so we can use u substitution. So letting u equal sine x, du is cosine x dx. And therefore we can write this as the integral of u squared by du. So that evaluates to u cubed on 3, plus the constant of integration, and substituting for u, we get sine cubed x on 3 plus c. Let's evaluate this integral. So here we have two functions that are not the derivatives of each other, and we can't apply further algebraic simplification, so we're going to integrate by parts. And what I'm going to do is select u is equal to x squared to reduce the power of x. So what we get is du is 2x dx, and dv is equal to cosine 2x dx, and therefore v is equal to 1/2 by sine 2x. And multiplying u by v, we get x squared on 2 by sine 2x minus the integral of v multiplied by du. So the 2's are going to cancel, and we get x by sine 2x dx. And now you can use integration by parts again to evaluate this integral, and then combine it with this result, add the constant of integration, and post your answer in the comments. Let's evaluate this integral. So the indication is that the sine and cosine functions are derivatives of each other, so we can apply u substitution if we do a bit of algebraic manipulation. So what we're going to do is use trig identities to write cosine cubed x as cosine squared x by cosine x. So cosine squared x is 1 minus sine squared x by the trig identity, and multiplied by cosine x integrated with respect to x. And now we can let u equal sine x, then du is cosine x dx. So we can write the integral as u squared by 1 minus u squared by du. And we can split this integral as the integral of u squared with respect to u minus the integral of u to the 4 with respect to u. And therefore this becomes u cubed on 3 minus u to the 5 on 5 by the power rule, plus the constant of integration, and then you can plug in for u and get your final result. This integral has functions that are not derivatives of each other, and it can't really be simplified algebraically, so we're going to apply integration by parts. And if we integrate either term, well, they're just going to go back and forth indefinitely. So what we'll do is just simply set u to either one of them. So u equals sine x, and du is thereby cosine x dx, and dv is e to the 3x dx, and therefore v is 1/3 e to the 3x. And we multiply u by v, so it'll be 1/3 e to the 3x sine x minus the integral of v du. And now we can apply integration by parts again in a similar way to evaluate this integral, and then the integral will be in the form of e to the 3x sine x, and then we set this result equal to the original integral and then solve for this integral to obtain the final answer. So post your answer in the comments. Let's evaluate this integral. So sine x and cosine x are derivatives of each other, so we can use u substitution. So setting u equal to sine x, du is cosine x dx. And therefore we can write the integral as u to the power of 32, integrated with respect to u. And therefore, using the power rule, we obtain u to the 33 on 33, plus the constant of integration. And then substituting back for sine x, we get sine x to the power of 33 on 33 plus c. Let's evaluate this integral of arcsine of x. Well, we know how to differentiate arcsine, so what I'm going to do is use integration by parts. So u equals arcsine x, and therefore du is 1 over the square root of 1 minus x squared dx. And therefore dv is dx, and v is equal to x. So we multiply u by v, which is x by arcsine of x, minus the integral of v multiplied by du, so that'll be x over the square root of 1 minus x squared dx. And now you can evaluate this second integral here by u substitution and post your answer in the comments. We have an integral of a rational polynomial function with a higher degree polynomial in a denominator. So what we're going to do is use partial fractions, but first we need to factorize the denominator. So we can write 8 as 2 cubed, and now we can use cubic factorization to factorize the cubic. So I have x minus 2 multiplied by x squared plus 2 by 1 by x, and then plus 2 squared, which is 4. And now we can write this in partial fraction form. So we have a linear factor, and then plus the irreducible polynomial. So we plus bx plus c on x squared plus 2x plus 4. And now you can apply your usual method of partial fractions to obtain these coefficients and evaluate the integral and post your answer in the comments. Let's evaluate this integral of a rational polynomial function with a higher degree polynomial in a denominator. So we'll use partial fractions and take the constant outside the integral first. So inside the integral, we need to factorize the denominator. So we have 2x squared plus 5x minus 1, and we're going to use cubic factorization to factorize this cubic. So we'll write the 1 as 1 cubed, so we have x minus 1 multiplied by x squared plus 1 multiplied by the coefficient of x multiplied by x, and then plus 1. And now we can equate this with some constant over this linear factor, and then plus bx plus c on this irreducible polynomial. And now you can apply your usual method of partial fractions to obtain these constants, then evaluate the integral and post your answer in the comments. Let's evaluate this integral with the same degree polynomial in the numerator and the denominator. So we can apply polynomial long division. We'll just use some simple algebra first. So we have 2 plus x squared, and then subtract the 2, and we don't alter the integral. So now we can write this as the integral of 2 plus x squared on 2 plus x squared, which is 1, evaluated over x, and then minus the integral of 2 on 2 plus x squared, integrated with respect to x. So this can be evaluated quite easily, and this integral is going to evaluate to an arctan. So have a go at doing this, and post your answer in the comments. Let's evaluate this integral. So our option is to use integration by parts, because we know how to differentiate arcsec. And du is equal to 1 over the absolute value of x by the square root of x squared minus 1 dx, where x is going to be greater than 1. And therefore dv is dx, and v is equal to x, and therefore we can write the integral as x by the arcsec of x minus the integral of v du. So x is going to cancel, so what we get is 1 over the square root of x squared minus 1 dx. And now you can evaluate this integral using trig substitution, and have a go at doing that, and post your answer in the comments. Let's evaluate this integral. So what we're going to do is apply integration by parts, because we know how to differentiate arctan. So du is equal to 1 over 1 plus x squared dx. And therefore dv is dx, and v is equal to x. So we can write the integral as u multiplied by v, so that'll be x by the arctan of x, minus the integral of v du. So that'll be x on 1 plus x squared dx. And now you can evaluate this integral using u substitution, and post your answer in the comments. Let's evaluate this integral. So first we're going to apply trig identities to simplify the cosine. So we have sine x to the power of 100 by cosine squared x by cosine squared x by cosine x dx. And now we can use trig identities. So we have sine x to the 100 multiplied by 1 minus sine squared x, so that's cosine squared x, and we square that by cosine x dx. And now you can easily apply u substitution to evaluate this integral, and post your answer in the comments. Let's evaluate the integral of sec x. And if you tried integration by parts, you're going to make the integral worse, because the derivative of sec x is equal to sec x tan x, and we also know that the derivative of tan x is sec squared x. So what we're going to do is try to get this in a form where we can use u substitution. So we can add these together and write sec x multiplied by tan x plus sec x, and to leave this integral unaltered, we're going to divide through by tan x plus sec x, and this is integrated over x. And now if you set u equal to tan x plus sec x, then du is sec squared x plus sec x tan x. And now you'll be able to easily evaluate this integral by completing the u substitution. Let's evaluate the integral of sec x to the power of 4. And because it's an even power, we can write this as sec squared x by sec squared x dx, and use a trig identity. And dividing through by cosine squared x, we get 1 plus tan squared x is equal to sec squared x. And therefore we can write the integral of sec squared x by 1 plus tan squared x over x, and therefore we can set u equal to tan x, then du is sec squared x dx, and now you can write the integral of 1 plus u squared with respect to u, and you can complete the u substitution now quite easily. Let's evaluate this integral. So u is equal to the natural log of 3x squared plus 1, then du is equal to 6x on 3x squared plus 1 using the chain rule, and therefore dv is dx, and v is equal to x. So we have u multiplied by v minus the integral of v du. Now what we can do is take 2 outside the integral, so we end up with 3 here. And now you can do a bit of algebra by adding 1 and subtracting 1, And what you'll get is this integral in the following form. So you'll have 2 by the integral over x, and then minus the integral of 1 on 3x squared plus 1. And you could have obtained this using polynomial long division also. So you can evaluate this one quite easily. And this integral here evaluates to 1 arctan. So have a go at evaluating this, and then combine it with this result, and post your answer in the comments. Let's evaluate this integral. So if we use integration by parts, this integral is going to get more messy, because the derivative of cosec x is equal to minus the cotangent of x by cosec x. And we also know that the derivative of the cotangent of x is minus cosec squared x. So therefore we can rewrite this integral by factoring out cosec x and adding these two derivatives together. So what we get is minus outside, and to leave this integral unchanged, we need to divide through by minus the cotangent of x minus cosec x. So in other words, this minus is going to cancel. And now we can use u substitution by setting u equal to the cotangent of x plus cosec x, and therefore du is minus cosec squared x minus cosec x by the cotangent of x. And now you can easily complete the u substitution and post your answer in the comments. Let's evaluate this integral. So because it's an odd power, we need to rewrite the integral and use integration by parts. So we have u is equal to cosec x, then du is minus cosec x by the cotangent of x dx. And dv is cosec squared x dx, and therefore v is equal to minus the cotangent of x. So u multiplied by v gives us minus cosec x by the cotangent of x minus the integral of v du. And now we can apply our trig identity. So if we divide through by sine squared x, and now we can make this substitution for cotangent squared x. And now if you separate these integrals, you're going to get an integral over cosec cubed x. So effectively we've replaced this integral, and then we just subtract the result from here, and then equate the result with this original integral and solve for the integral of cosec cubed x. So have a go at doing that and post your answer in the comments. Let's evaluate this integral. So to do that, we're going to use trig substitution. So we have our typical trig identity, and we're going to set x equal to sine theta. So therefore dx is cosine theta d theta. And now we can substitute for x in the integral. So we have sine squared theta by dx, which is cosine theta d theta. And the square root of 1 minus x squared is the same thing as the square root of 1 minus sine squared theta. So what we have is the square root of cosine squared theta, which is cosine theta. And the cosine thetas cancel, and you can replace sine theta with the double angle trig identity. So 1/2 minus 1/2 cosine 2 theta d theta. And now evaluate this integral, sub back for theta, and you'll get your answer in terms of x. And post your answer in the comments. Let's evaluate this integral. So here we can apply the double angle trig identities. So 1/2 minus 1/2 cosine 2 theta, so that will be 6x, and that's multiplied by 1/2 plus 1/2 cosine 2 theta. And we're integrating with respect to x. So we can expand and simplify. So we have 1/4 minus 1/4 cosine 6x squared, integrated with respect to x. And now you can apply the double angle trig identity again, and evaluate the integral and post your answer in the comments. Let's evaluate this integral. So what we'll do is use our typical trig identity, and to get this in the form of 1 plus x squared, we're going to divide by cosine squared theta. And we'll set x is equal to tan theta, and therefore dx is sec squared theta d theta. And substituting for dx, we get sec squared theta d theta. And substituting for x squared gives 1 plus tan squared theta, which is sec squared theta to the 5/2, or sec theta to the power of 5. So this simplifies to 1 over sec cubed theta, which is the same thing as cosine cubed theta, or cosine squared theta by cosine theta d theta. And now you can substitute for cosine squared theta using this trig identity, and then use u substitution to evaluate the integral. Substitute back for theta and post your answer in the comments. Let's evaluate this integral. So applying integration by parts is going to make this more difficult to evaluate. So what we'll do is use dummy variables. So I'm going to say w is equal to e to the power of x to the third. And if we take the natural log of both sides, we obtain x to the third, and then cube both sides, we get x is equal to the natural log of the dummy variable w cubed. And therefore dx is equal to 3u squared by du dx, which is w in the denominator, using the chain rule. And we evaluated this with respect to w. And now we can substitute for e to the power of x to the third, so that's w, and dx is 3 on w by the natural log of w squared. And this cancels, and now you can use integration by parts, and we've evaluated the integral of the natural log previously, which you can use here, and then after you evaluated the integral you can sub back for w and get your answer in terms of x, and post your answer in the comments. We have the integral of the product of two functions, so we'll use integration by parts. And we don't want to integrate arc cotangent, so we're going to set it to u so we can differentiate it. And we know the derivative is minus 1 on 1 plus x squared dx. And dv is x squared dx, and therefore v is equal to x cubed on 3. And then multiplying u by v, we have x cubed on 3 by the arc cotangent of x minus the integral of v du. So minus minus is a plus, and we take 1/3 outside the integral, and x cubed on 1 plus x squared dx. And now the degree of the polynomial in the numerator is greater than that in the denominator, so you can use polynomial long division to evaluate this integral, and post your answer in the comments. Let's evaluate this integral, which looks a bit tricky to apply integration by parts. So we'll try to put it in a form where we can apply u substitution. So what I'm going to do is just multiply by e to the x on e to the x, and we don't alter the integral this way. So if we take the 4 outside the integral, so we have e to the x in the numerator, and then e to the minus x by e to the x is 1, plus 3e to the x, integrated with respect to x. And now we can set u equal to 1 plus 3e to the x, and therefore du is 3e to the x dx, and this integral becomes 4 by the integral of 1/3 du, so divide by 3, and then in the denominator we have u. So that's equal to 4/3 by the natural log of u, which is 1 plus 3e to the x plus the constant of integration. Let's evaluate this integral. So the degree of the polynomial in the numerator is lower than that in the denominator, but we need to factorize the denominator to use partial fractions. So to do that, we'll use a difference of squares. So x squared minus 1 by x squared plus 1, and we can further factorize the first factor. So what we have is x minus 1 by x plus 1 by x squared plus 1. And now we can apply partial fractions. So for the linear factors, we have a constant a and a constant b, and for the irreducible quadratic, we have a constant c by x plus another constant d on x squared plus 1. And now you can multiply through by the denominator and use a typical method of partial fractions to obtain these constants, and the integral then becomes a lot easier to evaluate in this form.